Okay, so let's start with page 2 in your packet. So the page 2 in your packet is really crucial in this unit because it basically serves as a cheat sheet, as a resource page, and it includes all the little details about balancing chemical equations, the things you should include in balancing chemical equations, stuff like that. So whenever you are encountering a difficult problem, always refer back to this page. It probably has what you need. Okay, so the first thing I want you to notice is that all of the reactants and products, so basically all the molecules in your chemical equations, should have a state of matter afterwards. So for example, for copper, right, it's a solid metal in room temperature, so that it should be written as copper, parentheses S for solids. And if you just have elements, right, single elements like copper, you should be reading the laminated sheets of periodic tables based on the color font of each element. It should tell you what the state of matter is. And you have to remember your 7 diatomic molecules. Here they come back. So for example, bromine, right, instead of existing as Br, it exists as Br2 and is actually a liquid during room temperature, so Br2 should be a liquid. Okay, and all the acids are aqueous unless otherwise noted. Aqueous just means that they're dissolved in the presence of water. Okay, so then to start out balancing the equations, you want to perform an atom inventory. So basically you're counting how many atoms you have on each side based on their identity, and we'll see what that means in just a second. And when you're balancing the equations, you can only change the coefficients in front of a formula. Okay, so that means just like in math, if you have x plus y, you cannot change what they are, right? But what you can change is what goes in front of these variables or formulas in our case. Okay, so this number, the coefficient in front, is what we will change in balancing our chemical equations. We're changing how many of each formula we have. We never change what these are. Okay, if it's a polyatomic ion, it stays. If it's just an atom, it stays. So whatever is given to you, they should stay. Okay, so the first step is we want to begin with an atom that appears only once or the least amount of times on the left side and the right side, and we want to do H and O last. Okay? If we ever have polyatomic ions that is the same on the left and right, we want to just keep them. Okay, we don't want to separate them into different atoms. And all the coefficients must be whole numbers, and they should be in their lowest common factor, meaning they are simplified. Okay, so let's do a few examples. I'll start with the easiest one. So this over here is like our inventory, right? We're counting how many lithium we have on each side and how many oxygens we have on each side. So starting out right now, on the left side of the arrow, we have the reactants. Okay, and on the right side of the arrow, we have our products. Okay, so on our reactant side, we have 1 lithium, right? And we have 2 oxygens. That's based on the subscript 2 after the oxygen. And on our right side, we have 2 lithiums and 1 oxygen from lithium oxide. So right now we can see that the lithium number is not balanced on the left and on the right, right? On the left we have 1 lithium, while on the right we have 2. So what we're going to change is, instead of making this coefficient 1, right? That's what we currently have. I want it to be, maybe let's try a coefficient of 2, right? So once I change that, now I have 2 lithiums on the left because of that coefficient. Right? Okay, so now I balance my lithium. I'm just going to go in and do the same thing for my oxygen. So this time I want the right side to have 2 oxygens at least, right? So I'm going to put a 2 over there, and what we have to be careful is this is like a distributive law in math. Okay, so whatever we do, 2x plus 2y, we have to distribute to everything in there. Okay, so while we make 2 oxygens, right, we're also making 4 lithiums on the right. Okay, because 2 times 2 is 4. Okay, so now I'm going back to the lithium step, and I'm changing my lithium to 4. So now I'm going to be like, okay, now I have to go back to the left side and change how many lithiums I have. And I'm just going to put a 4 over there, right? Now my whole thing is balanced. Note that there is a 1 actually written in front of the oxygen, but we just don't write it out. It's like in math, you never write 1x, right? You just write x. Okay, let's move on to the second one. Let's create our inventory. I see that my Fe, my iron, only appears once. So that's going to be the first one I do. And then I'm going to move on to my H's and my O's. In this case, it doesn't really matter because they're fairly simple terms. Okay, so on our left side over here, we have 2 Fe's, while on the right side, we have 1. Okay, and if I count my H's, I have 2 H's on the left and 2 H's on the right. Okay, so that H is done. We have 3 oxygens, and on the right side, I currently only have 1 oxygen. Okay, so to start out, I'm just going to fix how many irons I have on the right by multiplying that iron term by 2. Okay, and then my H is done. I can move on to the bottom for my oxygens. Okay, so I'm going to multiply this by 3 because I know that I need at least 3 oxygens. Right, I changed this one, but I also have to be careful when I'm changing that coefficient in front of my H2O. I'm also changing the number of H's I have on the right, right? So 2 times 3 is 6. I have 6 hydrogens on the right, okay? And now the left side needs another number in front, and that gives me 6 hydrogens, okay? So now everything should be balanced to Fe, 6 hydrogens, and 3 oxygens, okay? So moving on, here we can see a few of those polyatomic ions, right? Those ones, if they appear both on the left and right as the same exact thing, right, we can keep them. So that's why we have NO3 and SO4 written separately instead of like, oh, how many N's, how many O's, how many S's, how many O's, okay? So we're just going to keep them when they are identical on the left and right. So on the left, I have 1 Pb. On the right, I also have 1 Pb. I have 2 NO3s, right? That 2 only goes for the NO3 and not the Pb, okay, because it's written after the nitrate. So on the right side, we have only 1 nitrate. On the left side, we have 2 hydrogens, and on the right side, we have 1. Left side, 1 SO4, and on the right, also 1 SO4. Okay, so my Pb is done. I'm just going to go straight to my NO3 and putting that coefficient in front of my HNO3, right? That changes my NO3 number to 2, and it also changes how many H's I have, right? So now I have 2 H's, and if you check everything, everything should be balanced out. So this is exactly what our equation for this reaction will look like. Okay, moving on to this very, very complicated looking equation. We have Na, okay, we also have PO4, which is one of the polyatomic ions. We have also Fe, let's write that down. have chlorine, and we also have our PO4. Okay. So I think in this case, it doesn't really matter which order we do them in because they only appear once for both. Okay, so I have 3 NAs on the left, one NA on the right, one Fe on the left, one Fe on the right, 3 chlorines on the left from over here, and 1 chlorine, 1 PO4 and 1 PO4. Okay, so I'm going to start with my Na by multiplying this Na term by 3 to get what I want. That also gives me 3 Cl terms, right? I'm distributing this 3 to both. Okay, so that looks good already. Okay. Okay, so the last one we have a combustion reaction. So when you see a bunch of C's and H's and O's, it tends to tell you that the numbers are going to go back and forth a little bit. So starting with my C's, going down to my H's and O's. Okay, so let's start by counting how many H's we have on the left, 1 C on the right, and 6 H's, and 2 hydrogens on the right, 2 oxygens, and we have 3 oxygens on the right, right? We have 2 here and 1 here. Okay, that's how we get our 3. So, starting with the carbon, I multiply this carbon term by 2. That gives me 2 carbons. And that also changes the numbers of oxygens I have, right? So this gives me 4 oxygens, and this still gives me 1 oxygen. So that is a total of 5 oxygens. Okay, and if I want to match my hydrogen now, I will have to multiply the right side over here by 3 to get 6 hydrogen. And now our oxygen number is changed again, right? So this gives me 4 oxygens, and this gives me 3 oxygens. So a total of 7 oxygens, okay? So at this point, I like to just put in on the left side that this oxygen needs 7/2, 7/2 as a coefficient in front of it. So that is from taking the bigger number on the right over the lower number on the left. Okay, so because if you multiply these together, 7/2 multiplied by 2 in the oxygen, we actually get 7, right? So that will give me 7 oxygens on the left if I put that number in there. Okay, you just have to remember that number is from taking the bigger number on the right over the smaller number, usually a 2, okay, on the left. So now I think all of our answers should be matched, right? But we have to do a sanity check because one of the steps in here said all the coefficients must be whole numbers, right? And that means we don't want a fraction in here. Okay, so what we're going to do is we are going to multiply every single term in this entire equation by the bottom number. Okay, we're going to multiply every single thing by the bottom number. Okay, so that gives us 2 over here. 1 times 2 is 2. And when you multiply 7/2 by 2, you should be able to get 7. Okay, and then we multiply the next coefficient by 2. 2 times 2 is 4. And the next one is 3 times 2 is 6. Okay, so this should give us everything in its least common multiplier or factor term. Okay, so on the next few pages there are some examples, so I want you to try these and make sure you're doing your inventory and make sure that you are calculating all your numbers correctly.